All right. So this video covers a few things. And to begin with, let's. The first thing I need to do is to explain how to find the inverse of a transformation. Like we have previously discussed, that a transformation is just a function, right? So functions do have inverses in case they are a bijection. Okay, so that is what we are going to discuss. Let's define a function, a transformation from three-dimensional space of real numbers to polynomial space of degree less than equal to 2, right? And this transformation is defined as g of x y z equals okay, this is y plus z plus x plus 2y plus 2z, sorry, 2z into t plus x plus y times t squared, right? So this is what we have been given. So yeah, you know the dimensions of a polynomial space. 1, in this case t, and t squared, right? So this is what this linear transformation is doing. Okay. Okay, let me just take a quick example. 1 0 0 is a basis for our domain. So this is a vector in our domain. Okay, what will it do? Y plus z is 0 plus x plus 2y plus 2z is just 1 plus x plus y is also 1, right? So g of 1 0 0 is t plus t square, right? This is the transformation that is happening. Okay, so our three-dimensional vectors are being mapped to polynomials of degree less than equal to 2, right? Quadratic polynomials. Okay, now how would we define the transformation matrix? Pretty simple. Okay, like this is the coefficient of 1, which is our first basis. This is the coefficient of the second basis, and this is the coefficient of the third basis. So I just write the coefficient of, like, the coefficient of x here, coefficient of x is 0, coefficient of y is 1, and z is 1. Similarly here, x is 1, 2, 2, and then here we have 1, 1, and 0. And in the background, I have dogs, so just ignore them. Okay, my bad. This is not what's happening. Okay, so here I have x, y, z. And these are being mapped to these, right? Yeah. Now, so what can we evaluate from this matrix? Let's reduce it to echelon form and see what we get. Okay, I'm replacing third and I'm putting third row in the first position. Then I'm writing the first row in the second position, and then I'm subtracting this from this. 1 minus 1 is 0. Oh, my bad. 1 minus 1 is 0. 2 minus 1 is 1, and 2 minus 0 is 2. Okay, so what next? Next I will do R3 changes to R3 minus R2, right? So I get 1 1 0, 0 1 1, and 0 minus 0, 1 minus 1 is 0, 2 minus 1 is 1. Okay, so this is what I get. And I get 3 pivots in my transformation matrix, which implies that the rank of G is my transformation matrix, okay, is 3. It is a full rank matrix. Okay, what this means is that the nullity of G is 0. Okay, there is no vector in our domain that is mapping to 0 apart from 1 0 0 0 vector. Okay, no other vector is mapping to 0. So what this implies also is that the kernel of G is just the 0 0 0 vector. Okay, this is the only vector in the kernel. Okay, but the nullity of G is 0. Okay, and the rank of G is 3. Also to observe, a thing to observe is that the dimension of our domain and range is 3. Okay, now what this implies is that the dimension of domain and range is 3, and the transformation matrix is a full rank matrix. Nullity of G is 0. That means kernel of G contains only the 0 vector. All these things conclude that our transformation is non-singular. Also implying that this matrix we got, transformation matrix, this is invertible. Okay, and this matrix is also non-singular. That means our transformation is also non-singular. Okay, now this non-singular is a condition that points to the existence of the inverse of a transformation. It is not a guarantee, but if the transformation is non-singular, then there are chances that it will be invertible and the inverse would exist of the transformation. Okay, let me give you an example here, a quick example. Okay, f x y z. Yeah, okay, see, we have x plus y plus z. This is z, then 2x plus 3y plus 5z, and then x plus 3y plus 7z, x plus 3y plus 7z. Okay, is that the example I intended to take? Okay, let's form the transformation matrix. 1 1 1 2 3 5 1 3 7 2 3 5 1 3 7. Okay, I'm doing it quick. Okay, 1 1 1 negative 2 times 0 3 minus 2 1 5 minus 2 3 1 minus 1 0 3 minus 1 2 7 minus 5 6. Okay, see, 1 1 1. Okay, no, this is not a concrete example. I'm sorry. This is okay. Since I've done this much, see, the transformation matrix is singular matrix. The determinant is 0. Kernel is not empty. Nullity, wait. Nullity of f is 1. Kernel of f is not empty. Okay, I mean, it's not even just the zero vector. It has, I should not write this, it is never empty. This 0, 0, 0 is always present in the kernel. Okay, so dimension of kernel of f is more than 1. Am I right? No, I don't think I'm right. Dimension of kernel of f is 1 actually. Okay. That means there is a vector other than the zero vector which is mapping to 0 in the range space. Okay, so in this case what we will imply that such a transformation can never be invertible. Okay, this transformation can never be invertible. Okay, and what I was trying to explain is that it is possible that we get a transformation matrix which is a full rank matrix, but still say we are going from R4 to R3 or R4 to R5. Okay, say this is the case and we get a non-singular matrix. Even then we cannot have an inverse transformation. Okay, because for a transformation to have an inverse, the dimension of domain and range should also be equal. Okay, this non-singular thing only implies that it is 1 1. It has to be onto also. Okay, again I'm sorry for, oh no, this helped. I hope this helped. Okay, so this matrix being non-singular points to the fact that our transformation is 1 1. Okay, also this points to the same fact. When the kernel of G is only zero vector, it points to the fact that the transformation is 1 1. But then the dimension of the domain and range should also be equal in order for the transformation to be onto as well. Okay, and when it is a bijection, only then we will conclude that the transformation has an inverse. Okay, which in this case exists, and let's find it. Okay, so how to find it? Okay, we'll assume, see, I'll assume this thing to be A, this thing to be B, and this to be C. Okay, also I'll copy this. No, I can't. Okay, I'll write it again. That's okay. Just you come back and see. This is A, this is B, this is C. So that means G of x, y, z is A, B, C, where A was x plus y, B was what was B? X plus 2y plus 2z. Okay, even A was y plus z. A was y plus z, B was x plus 2y plus 2z, and C was x plus y, right? Let me confirm it. Yeah. Okay. Now, just as we used to find the inverse of a function, it is the same method. Okay. Just solve these equations and all these three of them, all three of them. Okay, so like, okay, let's solve it. I'll name this as 1, this as 2, this as 3. So what I'll do is I'll write 1 and 3. Okay, 1 is this, and 3 is c to y plus x. Let's subtract. So a minus c is z minus x. Why did I even do this? Okay, yeah, a better thing was this. 2 times equation 1. Let me write that. 2a equals 2y plus 2z, and then I'll subtract second equation from this. b is x plus 2y plus 2z, and I'm subtracting this equation, so this will cancel out, this will cancel out. I'll get 2a minus b equals negative x, or x is b minus 2a, right? Now x is b minus 2a. I will plug this value in equation 3. So my y is c minus x, y is c minus x, and I'll plug this value of x here. So this is my y, and okay, nice. Z is this, okay, a minus c plus x, which is a minus c plus x is b minus 2a. So this turns out to be minus a plus b minus c. Okay, so g of xyz is abc. That means, this means g inverse of abc is xyz, right? And what is xyz in terms of abc? X, y, and z in terms of abc. And this is our inverse transformation. So we'll write g inverse of xyz is, okay, instead of xyz, it doesn't matter, by the way. You can replace the variables. Since I took abc, I write as, okay, my x is b minus 2a, y is 2a minus b plus c, and this is minus a plus b minus c. Okay, you can put x, y, z here, and like yx here, x, y, z, corresponding values. It won't make any difference. These are just variables, right? Did I confuse you? Okay, let me just do it then. It will be y minus 2x in terms of x and y. 2x minus y plus z, and minus x plus y minus z. Okay, so in terms of x and y, x, y, and z, this will be the inverse transformation. That is how we find inverse. Okay, the important part in this was when to conclude that inverse exists. Transformation matrix is a full rank matrix, implies, okay, the transformation is 1 1. Then if the dimension of range and domain and codomain is same, that means it is on 2 as well. And that is when we can conclude that, okay, the inverse transformation exists, and this is how we find it. Any doubts, just ask me, or watch it again, or ask me, yeah, in the comments. That's it.